Hello. So we will try to solve the problems for the chapter 2 of volume 3, geometrical optics and then image formation. Okay, so problem 28. A doctor examines a mole with a 15.0 centimeter focal length, magnifying glass held 13.5 centimeters from the mole. What is this magnification? But the image can be either upright or inverted. So in this case, we need to uh, uh, apply the lens law, lens equations. It's given DO is objective distance, DI is image distance. So in this case, we have what is given. What is given here is that uh, we have a DO is 13 centimeters. And then focal length is also given, F is given. And then we want to find out what is its magnification. In order to get the magnification, we need to find out the DI, the image distance. Okay, so for given F and DO, objective distance, we can find out DI, and then DI is this one. And once we have a DI, then we can get the magnification formula, which is given by this one. Okay, and then we can find out what it is. 13.5 versus minus 135, factor is 10. Okay. Problem 30, the focal length of a concave mirror. Now we are talking about mirror. Focal length is given. Object is located at 30.7 centimeter in front of the mirror. So that object distance is given. How far in front of mirror is the image located? We want to find out image distance. Once again, you will find out the mirror equation and the lens equation is identical. But in the case of this case, F is given, object distance is given, then you can find out DI is given like this. And then from this, we get DI, image distance. It's very direct application of the mirror equations. The next questions, an object of a height 5 centimeter is placed at 5 centimeters in front of a converging lens. So the height is given, and then there is a object distance is given, and the focal length is given. Observed from the other side, how large is the image? So we want to find out the magnifications, specify whether the image is upright or inverted by the sign of the image height. Okay, so let's see how it goes. The lens equation is this. So F is known, DO is known, and such that, and DI is found here. Okay. And the magnification should be this side, because it is on the same side, so that we get a minus sign. And then image height is given by HI is this times this, so that we have this value, okay? So it's basically, you have these equations here, and then magnification is nothing but this formula, and then we get this one. And from the magnification, this minus side, this is inverted, okay? Next problem, the lens to retina distance is 2 centimeters. The print in many books average 4 millimeter in height. This is the object height. Find the size of the image, magnitude only, of the print on the retina when the book is held 25 centimeters from the eye. So lens to retina distance is known. So that's the first thing we need to know. And then we have to come up with the object height, and then object distance. Okay. And note that this distance is actually, in fact, image distance. So image is formed at our retina, so that this tells us the image distance. Okay. And then what has to know further down is that we have a object distance is given by this one, and then once you know the image distance and the object distance, and then you can find out the magnifications. Okay. And then we can find out magnification from the DI and DO. Okay, here. Yeah. And then M is given. And then from the image height, you can get M is given by this one is this one. Then magnitude only is we have this. Okay. So that's the height that is on our retina. So for normal relaxed eyes, a magnifying glass produces angular magnification over 4. What is the largest magnification possible with this magnifying glass? So let's try to find out what it is. Angular magnification for relaxed eyes, image at the infinity. Image at the infinity is given by this one. Okay. This is the coming from the eye. And then here, angular magnification is given by 4 in this problem. And then 4 is known. We need to find out what the f, and then f is given by this one. And then maximum magnification. This part is a little bit tricky, and because there's a 1 plus this factor. And if you are not so sure about this, you need to read the textbook carefully, and then you'll find out this formula. It is well explained in the textbook, so please find out how it is derived. So, but note that this is the relaxed eyes is the image at infinity, M infinite is given by this one. From this, you get the focal point, and then now it's time to look at the magnification, maximum magnification at the near point is given by this one. Okay, and then f is now known, and then you can get this magnification factor of 5. Okay, so if you look at the formula, it's very simple, but you need to know how they are coming from. So that please read the textbook once again. P40, where does an object need to be placed relative to the microscope lens for its 0.5 centimeter focal length objective to produce magnification of minus 330? So in this imaging optics, you have two formulas usually used. So you have a lens law or mirror's law that relates the object distance and the image distance with the focal length. And that is one formula. And the other one is the magnification formula. Okay, so that's the two major formula you need to apply. So here, magnification formula is this one. So you DI, image distance, DO, like this. And then what is given here is the magnification is already given, and that this is the case. So the DI is 370 times DO. And then using the lens equation here, so you get the DO, DI, and then you get this relationship. And then simplify, then you'll get 1 over f is given by this one. And then focal length is given 0.5 centimeters. And then the object distance is found. So once again, what is what we are doing is based upon two formula, magnification formula and the lens formula. Consider converging lens in the in figure below. It has a focal length of f1. The lens has f1, and then object is placed in distance of 25 centimeters to the left. It's the object here. In addition, there is a concave mirror with the focal length of f2 is 9.9 centimeters. Okay, so from here to here is the 9.9 centimeters. From here to here is 17.9 centimeters. So in this case, what is happening here is that first, this object is going to give you a certain image, and this image will be an object for this mirror. So you apply the lens law and the mirror law in a sequence, and then you can find out the final images. The first image formed by the lens, okay, is can be found using the lens equation, okay, and then di is found here, and so di is 63 centimeters. Okay, di is 63 centimeters. And then this image acts as an object for the mirror. This is the object. So L minus di. So here is the L minus di is where the object is formed from the mirror. Okay, so that it should be L time minus di is the object. There should be object distance. Okay, so and then so if it is, note that di is reference to the lens. Okay, reference to the lens somewhere here. And then this should be converted to the object distance so that the distance from here to here is important. So this is L minus di. This is the very critical step. So, and then you get the object distance for the mirror. And then you apply the mirror equations. And then you get the di2 is given by this one, which is this one reference to this position. Okay, so you need to understand what you are doing. So first you apply the lens equation to get the image location di, and then di is somewhere here, and then you need to understand this image serves as an object for this mirror. Okay, and the distance should be calculated from the mirror side to the this second object. So you should have L minus di is the right distance. And then position relative to the lens is given. So L is 125, and then second object distance to the lens is given by this one. And then you get final image given by this one. Okay. So there is several steps. So image formed by the concave mirror, we have this one. And then this position is relative to the lens. Then you can get you have this subtractions, okay? And then this serves as a second object for the lens, okay? This is the DO3, and then you get the DI3. So what is happening here is that this object is generate the image, and this image is generating another one, and then this serves as a third object for this lens. So there's a three image formation law. So one is the lens equation for this lens, And then this serves as an image. This serves as an object of the mirror, and then you get the image, di2. And then once again, this serves as an object for this lens to get the final image. Okay. So you have three steps. Suppose your 50 millimeter focal length camera lens is 54 millimeter away from the film in the camera. Okay. What is the height of the object if the image is 1.9 centimeter high? So once again, here is what is given the film. Film is the where the image should be located, so that the image distance is already given. Di is given. So, such as the eye cases. So you have an image distance is given, and then we have a focal length is given, and then image height is also given. Then utilizing the lens equations, so you can have a object distance, which is given this one. And then from the magnification formula, you get this one. And then finally, this is also related with the height, okay? This is the distance, and this is the height. And then once we find out the m, and then you can get a height object, okay? So once again, it is the combination of two formula. One is the lens formula and the magnification formula. And note that it is related to the hi over h naught. So distance or the height will give you the magnification factor. A light bulb is 4.1 meter from the wall. From here to here is the 4.1 meter. You are to use the concave mirror to project an inverted image of a bulb on the wall. So you're going to have a concave mirror, and then you have already given where the image is formed from here to here. Okay. And then there is a magnification is also given. How far should the mirror be from the wall? So here is the case. Geometry setup is that let mirror wall distance is x. So object is L equal to this one from the wall. And the distance from the mirror is given by object is given by x minus 4.1. Okay. So note that mirror wall distance is x. Okay, from the this one, then you can find out the bulb distance is mirror to bulb is x minus L, x minus 4.1. Okay, and then image forms on the wall. So image should be here. So di should be the x. Note that wall to mirror distance is x. So that what we know is that object, the light bulb is from mirror given by this distance, and then image should be formed at the wall, which is x. Okay, and the magnification relationship is that m equal to minus 1.75. Okay, and then if you change the do di into this formula, and then for the given number of minus 1.75, then you get this relationship. And then if you solve this equation in terms of x, then you get this final step, and then you can get the x. An object 7 centimeter high is placed in 13 centimeter to the left converging lens of focal length of 7 centimeter. Second converging lens of focal length 5 centimeter is placed 36 centimeter to the right of the first lens. From here to here is 36 centimeters. And both lenses have the same optic axis. Find the position of the image produced by the two lenses in combination. So once again, we are going to apply the lens formula twice. But here, if this object forms an image, this image serves as a object for the second lens. Okay, that's the sequences. So first lens, we have a f1 is focal length is given, and your object here is given. And then from this one, you get the image is known. From here to here is the 15 centimeters. And then this serves as object. And then here's the conversion, very important step. So you need to find out the distance from lens to the second image. Okay. Note that it is always reference to the lens. That this I1 is reference to the lens position to here. But in order to serve as an object, you need to convert the distance reference to the lens f2. Okay, so that this is what is happening. Lens 2 distance minus this image distance is actually, now you see that this serves as a object. Okay, and then you apply the second lens law, and then you will find out the di2 is this one. Okay. And problem 70 or object 7 is very similar to the first cases. Find the size of images produced by the two lenses in the combination. Previous case was trying to find out the location, but now it's time to think about the magnification. Magnification can be found by finding the image distance. Okay, step one is that the first lens will give you the image distance, di1, and then this magnification will give you this one, such that h1 of this image is given by this length. And then this serves as an object to the second lens. And then in order to solve that, DO2 should be this distance minus this distance, okay? So note that DI1 is given, and then from the DI1 to DO1, you get the magnifications. And then from this conversion, and then you get the DO2, and then the second lens equations. So if this, then you can get the DI2 here. And then once you get the DI2, then magnification is given by DI2 over DO2. So we have to think about the image and the second object and the second images, and then we get the magnification factor. And total magnification is M1 times M2, okay? And then it is given by this one. The final image height is this one.